Hello and welcome. This recording is session 2 of an 8-part series on the topic Moving Towards Improved Earthquake Performance and Resilience for New Buildings. My name is John Sherstobitoff. I'm a structural engineer focusing on earthquake engineering. This series of recordings is part of the MBAR initiative by BC Housing. It includes and promotes the consideration of resilience for new buildings for natural disasters such as earthquakes. The list of 8 sessions is noted on this slide for your future reference. This session is titled Earthquake Performance Options for New Buildings, Performance-Based Design. This is just a refresher from session 1 about the current objective-based codes. For normal importance buildings, the objective to minimize loss of life, but there will be extensive structural damage. High importance buildings, the objective of immediate occupancy to shelter in place, and post-disaster buildings to remain functional, but with no guarantee that that will be fully achieved. And there's a variation in performance due to these different ductility-related factors that can be selected for the seismic force resisting system. So variability of performance. So that's what the beauty of performance-based design is, to try and get a more definitive, quantifiable, understandable performance of the structural components, moving towards the target of no structural damage for different types of earthquakes. Performance expectations can be tailored and customized for each building depending on use, occupancy, expectations for business continuity, expectations of repair time and repair cost. And again, it can be owner specified as long as the basic code requirements are met. So this illustrates the difference between the 4 different levels of earthquakes where data is readily available on the Earthquakes Canada website. On the left, the bar graph on the left, the 2% and 50, the code level earthquake, 100% of the code level earthquake. 3 lower levels, more frequently occurring but lower intensity earthquakes. Designated as 5% and 50, 10% and 50, 40% and 50. Those are the probability of happening in those over those 50-year durations. And the different color bar graph shows the percent of demand relative to the full code level, 70, 50, 20. So reduced demand on the building as for these more frequently occurring but smaller earthquakes. And there's the ability to specify performance for all these 4 levels rather than just the one the code specifies. NBC 2020 has started to move towards performance-based design in certain sections for certain buildings. No structural damage is an objective for post-disaster buildings in moderate and high seismic areas where they need to behave elastically for that lower 5% and 50-year earthquake, with a reduced drift limit of 0.5% to better control damage to non-structural components. High importance buildings in high seismic hazard areas similarly need to behave elastically, but for a lower intensity 10% and 50-year earthquake with the same drift limit control. Plus enhanced connection design, no yielding of connections for the structural components. A no structural performance objective is also included for normal importance category buildings more than 30 meters high in the highest seismic hazard areas, but this is for the non-seismic force resisting systems and components of the building. They have to behave elastically for that lower intensity 10% and 50-year earthquake. So again, an owner can specify performance similar to these in the 2020 code for any type of building that they have. This slide illustrates the level of damage, for example, for post-disaster importance buildings. No structural damage for those 3 lower levels of earthquakes on the right, but still damage per code for the 2% and 50 earthquake illustrated with the red bar on the left. For high importance buildings and normal importance buildings more than 30 meters, they're non-SFRS components, no structural damage for the 2 lower intensity level of earthquakes shown on the right, but damage per code for the 5% and 2% and 50-year level earthquakes. And graphically, for the cartoons from previous sessions, for these groups of buildings, for the levels of ground motions noted, the blue bar indicates that no structural damage of performance expected. Again, not variable, consistent for those types of buildings. Performance-based approach can be used for alternative design, alternate to that specified in the code. Pre-approval should be obtained from the authorities having jurisdiction. It will require external peer reviews to suit the AHJ requirements. And this is now commonly done in the US for certain groups of buildings, and many BC firms are experienced in this approach. This shows there's very good guidelines and standards in the US, the first 4 documents shown on the left, to assist engineers and owners with performance-based design. On the right, EGBC has produced a similar guideline in BC for tall concrete buildings in 2022. So the performance-based design approach requires nonlinear time history analysis. It identifies the specific demands on the building components and to make sure they're behaving in the manner expected. In BC, 2 suites of 11 earthquake ground motions as part of that time history analysis. But there are performance-based guidelines in Canada, specifically for bridges. Again, that code has very specific performance requirements for different types of bridges and for 3 different levels of earthquakes. Very specific requirements for strain, stress, when concrete can spall, when it needs to be serviceability requirements, and the like. There's a significant initiative underway right now at Codes Canada to bring a full performance-based design into the NBC code for buildings. Perhaps some more provisions in NBC 2025 with an expectations of significant movement towards performance-based design in NBC 2030. So how does one measure seismic performance? FEMA P58, Seismic Performance Assessment of Buildings. It's a 7-volume document, and it has very extensive guidelines on procedures to assess performance. It's a probability-based assessment, and it can assess different scenarios or different methodologies. You can assess the damage and performance of an earthquake of a given magnitude at a given distance from your site. You can use response spectrum type approach similar to the design for new buildings, or it can be time-based, over say a 60-year period, all the possible earthquakes that could happen at that building to assess the performance of that building. The beauty is there's 5 key metrics: repair cost, repair time, casualty rate, the probability of being red carded, and to make sure indeed it is repairable after the earthquake. And it includes all the non-structural components. And the beauty of this is you can see which components of the building or the structure itself contribute to the repair cost or repair time. And the dollar figures in this one is the expected annual loss for a building, specific building. There's good tools available to do this kind of assessment. FEMA originally came out with a tool called PACT, but that has now been superseded by other software. SP3, it needs licensing on an annual basis. It includes impedance factors, which I'll talk about shortly, and it has a very good database and is constantly updated with good technical support. Ready rating system developed by Arup is similarly very effective at performance-based assessment. It's able to account for impedance factors as well. So impedance factors, very important to understand what these are because they do affect repair time and downtime. Things such as the time to get post-earthquake inspections done, financing in place, permitting in place, engineers mobilized, the contractor mobilized, and the impact of damage to utilities on the behavior and performance of the building. The table on the lower right shows that if no impedance factors are included, the downtime was estimated at 58 days. But when you include items such as financing or contractor mobilization, it could be in the order of 3 to 4 times longer. So very important to understand the durations for those factors. Similarly, the repair assumptions: can all floors be repaired in parallel, entire building at once, or in series, 1 floor at a time? And the table in the upper right shows an example that one building, it may take 2 months to repair in parallel versus close to 5 months to repair in series. So one has to be very realistic at the expectations of post-earthquake repairability. So in summary, performance-based design gives one a better understanding of the condition of the building after the earthquake. One can ask, what level of resilience do I want for the new building? Low repair costs, short repair time, ensure business continuity, shelter in place. And again, an owner can specify whatever requirements they want as long as the code minimums are met, such as the NBC 2020 provisions, or you can consider unique requirements for different portions of the building. You could create a refuge area with no damage, a functional area, and maybe part of it can be life safety that people can exit and get to the refuge area. Alternative to code designs can be used with a performance-based analysis to meet the code objectives and any additional owner-specified requirements. These tools and the skills are readily available in the structural engineering community today. So again, hopefully you'll consider a performance-based approach for your new building. The next session is on seismic isolation, which many consider the gold standard for seismic performance for new buildings. If you would like more information on this topic, please contact me at the email address noted below. For more information on MBAR, there's an email and webpage address noted. Thank you for attending this session, and I hope you join me again for more sessions in this series.